Hello everyone. Today I am going to teach you how to model a mechanical vibrating system using MATLAB Simulink. Before we start the modeling of the mechanical vibration system, let me show you a few slides to refresh our concept related to mechanical vibration. So here is just a simple example of a spring mass damper system. So here we can see that there are actually some basic component as shown. A spring mass damper system has a spring. So the spring is responsible for the storing of potential energy. We also have a mass present there. The mass is responsible for storing the kinetic energy. And we may have a damper in the system. And the damper is actually a means of destroying the energy. So overall, it decreases the system energy and hence the system stabilize. So the damper is there to waste some of the energy into the heat. So these are the basic three components. We can study such system in two cases. The first case is the free vibration. So the free vibration is the case in which there is no externally applied force. So actually we have an equation of the system, and each component of the actual mechanical system can be linked with this equation. So the first one is actually the inertial force, which is being developed at the mass. It's the inertia times the acceleration, ma. Second is the force, which is developed in the damper. It is the product of coefficient of damping into multiplied by the velocity. The third and the last component is the spring force. It is actually the product of spring coefficient multiplied by the position value with respect to the point O. And as this is an example of free vibration, so the system can only move due to the initial disturbance or the initial condition. So we have to provide some initial position or some initial velocity, and then the system is able to move. For such system, the free vibration actually takes place at the natural frequency of the system. So if we know the system parameter in terms of the mass, the spring coefficient, the stiffness, then we can find out the natural frequency. So in this case, there is no externally applied force and the system can only move due to the initial condition, and the system move at the natural frequency of the system. And this is also called the transient response. There is no steady state response in such system because there is no externally applied force. The second example is the force vibration, in which the system is same, but on the right side, we may have some applied force. And this externally applied force actually cause the system to move. So one of the example of such a force is a harmonically excited force. So the forcing function have some magnitude and some omega, which is the excitation frequency associated with this force. So this example, we are actually interested to find out the steady state response of the system. So in this case, the system is being applied with some external force. The system vibrates at the frequency of that of the applied force. And in this case, because there are two frequencies involved, one is the natural frequency of the system. The second one is the excitation frequency of the applied force. So in this case, there is a chance of resonance. If those two frequency matches, the system response increases, and then we call such a system as resonance. So before we go to the Simulink, I will cover this free vibration part. We need to rearrange this equation of motion. So this rearrangement is done. We actually keep the higher derivative term to the left side and we take all other forces to the right side. So this is the zero applied force, it's free vibration. This is the force due to the damping. This is the force due to the spring. And then we also bring this m on the right side. So the equation can be rearranged in this manner where x double dot is just a combination of those three signals. So if I graphically draw it, so it becomes this force, which is zero at this time. And then we have cx dot and then kx, and so plus minus minus signs correspond to the three signal. And if we divide this signal by m, it becomes the x double dot. So similarly, if we are interested to find out the velocity of the mass, we can actually integrate this signal with respect to time in order to get the velocity. And then this signal further can be integrated to get the position of the mass with respect to the time. Oh, here is just one example of the system parameter. So we are actually considering this as a general equation of motion, and then we are using those three values for a real life example. So we have the value of mass, we have the value of damping coefficient, and we also have the value for the spring constant. We want to simulate the system, and you can use this formula and you will find out that the system natural frequency is actually 10 radian per second, and the simulation will be carried out for those two initial condition where the initial position is 0.1 meter and the initial velocity is 0.1 meter per second. So let's jump into a Simulink now. So I'm opening a MATLAB and I'm opening Simulink here. So I click on the blank model and here a blank Simulink models open up. So I will show this presentation here and we'll take some the values which we are going to use uh, is given in this slide. So I go to the model browser and then I go to the Simulink. If we click on this link, it will open up this library browser independently outside of this. So here we can go to the commonly used blocks. So we can actually choose some constant, some gain that we will be using, some integrator, and then I am going to the math operation and I get this adder block. So my starter point is my starting point is right this block, right? So I need to generate three signal and then that will give me the x double dot. So in order to accommodate for the three component, I click on this block and then this sign open. So I'm going to type plus minus minus enter, and then it can actually accommodate three signal, and this output is so I'm going to connect those blocks to each other. I can make a copy of this integrator by right click and drag my mouse button. So, and here I need to divide this 1 divided by m. M is actually the mass of the system. And then I can go to the sync, take a scope. So now I need to take other signal for this. This is actually x double dot. Here I double click x double dot. This becomes x dot. Then this becomes x. So I'm also getting some value of this position being multiplied with a spring. So right here, I'm just making a copy of this gain and dropping into this line. And similarly, I need to do that one more time. So, and here, this is because this is the velocity. So this is going to be the C, the coefficient of the damping. You can also rename this gain with damping coefficient C, and this should be K as it is being multiplied with the position and then feedback to this to get the forces. So here I'm going to write spring stiffness. And because it is a free vibration, so the applied force is 0. So I type here 0. And this actually completes our model. But right now we have defined 3 variables as M, C, and K. But our system actually doesn't know about any variable. So because we have not defined it, so I'm going uh, to generate a blank script. And now I type and I define these variable at M is equal to 40 kg, K is equal to 4000, and C is equal to 200. So we can actually feed this into our workspace. So right now we see there are no variable defined on our workspace, but if I run this script, so we need to save this also. So I'm going to save it with the name of parameters and then run again. So we can see that those parameters are now available, and hence now we can actually run this model because now those M and C and K are known by your system. So if I run this button, so the simulation will run one time. And if I double click my scope, we should be able to see the position with respect to time. So here is the graph. So we see that the system is showing just 0 output because we have not put any initial conditions. So uh, we need to put those two initial condition for initial position the value is 0.01. So we can put the initial position data here. So 0.01 is the initial value of the position. And similarly, we can put 0.1 is the initial velocity here. And now if we run this again, so we can see this is now the system response. We can also go to the model setting and we can reduce this step size in order for this curve to be a bit more smooth. So from variable, we can go to the fix steps, and then we can also define from auto, we can say, let's say 0.01 is the fixed step size in time. So if we run this again, and now we can see the curve is more smooth. Similarly, we can do the plotting. So for plotting, we can actually go one more time to this sync for, and we can take to two workspace block. So two workspace block, double click this and take this as position, and then change this structure to array. And before we do this, we can also go to this model and we can go to the data, import, export, and uncheck this so that we can actually individually take all those data to the workspace. So this is the position. This is the velocity. And then we can also take one more to get the time. And now if we run this simulation, now we can actually plot this data. And so I have pre-written my plotting function. So I'm just copying and pasting this here. So the first one is about the time versus position. The second one is about the time versus velocity. So if we run this script or this section, so we get those two graphs. One for the position and the other one is for the velocity. Similarly, you can also change the value of uh, these damping coefficients. So let me copy and paste my script notes here. So you can see here, this is such a system. If you take the value of C uh, beyond 800, then the system behaves in an undamped manner, overdamped manner. So currently the value is 200, so it is behaving like an underdamped system. So we can also see this if I just remove this velocity, initial velocity, and now the system is only moving due to the initial position. And if I change this value to, let's say, 600, and I run this, so let me close those two, run again. So now the system is moving from the zero initial velocity. So initial velocity is zero now. And similarly, I can change the value of C beyond 800. So let me put it 900 and then run this section. And I need to change the color to red. for comparison purpose and run this section again. So before we actually change the values, we need to run the simulation one more time because the system will need to be updated. And now let me make it to this green color. So the new value will be for the overdam case. So now the system in this green is behaving with the overdam case. So the red one is the underdam system. We can see the system is, and the green one is the overdam. So I have this, I hope this helps. So thank you. Thank you for watching.